Hey guys, I want to make a little video on something called mass defect. Not sure you guys have seen this, and Kim, I don't know. So just talk about how mass defect works. On the screen here I've got, this is a little app representing uranium-235. And of course we can shoot a neutron at it and fission it, boom, and it should break apart into a couple different pieces. And that's pretty neat. But anyway, there's not a whole lot I can actually do to show you as far as a visual of mass defect. So I'm going to just talk about a couple things here. Hope I'm bigger now. So mass defect is often called missing mass, and it represents essentially the energy needed to keep a nucleus of an atom together. All right. I often think about this in terms of protons, electrons. Right. Protons are all positive, and so protons don't really want to be together, right? Because they're all positive. So it's fascinating that in the way that an atom works, all the protons are hanging out in the center there. And what's making them do that? Well, you have these amazing forces. You have the strong nuclear force that's holding them all in there, right? Without that force, well, I guess none of this stuff would exist. So anyway, atoms are made out of different pieces, and it turns out that the total mass of any atom and the mass of all its constituent parts are going to be different. And this has some really interesting implications. So I just want to talk about this real fast. A couple of things here. The masses of atoms are talked about in terms of AMU, which stands for atomic mass unit. Oftentimes people will use carbon as a good example, so I'm probably going to do that here. A lot of people like to use carbon-12. Carbon-12 is called carbon-12 because it has 6 protons, that's what makes it carbon, and then it also has 6 neutrons in the nucleus, and so 6 plus 6 is 12, so we call that carbon-12. Carbon-12 has a mass of essentially 12. So this is a thing. Now, it's really fascinating that if you break carbon-12 up into its little parts, that the mass that you get, if you add up all those little parts, won't be 12. And that's fascinating. See if I can make myself small. Okay. And so this is fascinating, right? So here's a picture here, and if you see on the screen, you have the nucleus here on the left side, and it doesn't have as big of a mass. That would be like your carbon-12. It has a mass of 12. And then if you break it up into all these pieces, you'll find that when you add up all these protons, neutrons, yada, 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 you're going to get something greater than 12. You get like 12.09, 12.08, something like that. And so this dumbfounded people for a long time. They thought, well, there's something missing. There's mass missing. And so they call this mass defect or missing mass. And what it is frankly, it's an application of, make myself bigger again, it's an application of, you guys know, the most famous equation. Well, heck, the most famous equation ought to be F equals ma, right? That ought to be it. And Einstein would probably agree that, Newton is kind of a big deal. But if you ask people on the street, what equation is the most famous equation, they're going to say, that one. That's the most famous equation. Oh my God. And so this is what's going on here is essentially this is an equivalency. One side of your equation is equivalent to the other side. Are they the same? No. They're equivalent. So energy is equivalent to mass, is what this is saying. Right? Now, Einstein, the dude who figured out a lot of this stuff. See if I can make myself smaller again. I keep making it bigger and smaller. So Einstein was the guy who figured this out. And here you go. These are the notes I put in the module, so you can go and take a look at these. And here again, this is shown by his famous equation on the screen. E equals mc squared, right? And so what happens is that when you put atoms together, it takes a certain amount of energy to keep them together, and we call this binding energy. And of course, you can rip atoms apart. And when you rip atoms apart, that energy is unleashed. And we know this because this is what makes nuclear weapons a thing, right? So when you set a nuclear bomb off, you get all the death and destruction and light and heat and sound, and all those things are this binding energy, right? So that would be like a fission bomb. And you get to see all of this energy. And of course, that represents all of the energy that keeps the atom together. Okay. All right. So anyway, I'm going to do a little example here to show you how this works. So let's say we have our carbon-12. And carbon-12 is called carbon-12 because the mass of carbon-12 is 12, right? It's actually 12.00 something, but for the most part, we'll just say it's 12. Okay. Now, the strange thing is what we're going to do, we're going to hunt for the mass of a proton and the mass of a neutron real quick. So I'll make myself smaller. All right, so I just Googled this because that's what you do now when you look, when you need to know something, you Google it. So according to Google, the mass of a proton is 1.00727 AMU. I'm going to write that on my board. Y'all can see me. That's the mass of a proton. Mass of a neutron is something around 1.00866. I'm not being particularly super precise here. Just going to give you the gist of it. Okay. Make myself big. So, those are the masses. And this little bit extra here doesn't seem like much, but it will be. All right. Now what we're going to do is, since there's 6 protons and 6 neutrons in carbon-12, we're going to multiply this by 6 and multiply that by 6. So I got to get my calculator because math and I don't always get along. Y'all know this. So for the proton, I got 6.04. That's a 3. And then for my neutron, I got 6.05196. Those are my masses, right? Now, the interesting thing is, now what we're going to do is over here, we're going to add these two up. So we're going to add those. Hope my board doesn't fall. That'll be hilarious. So I'm going to add those. I get 12.09558. So notice, there's a difference between carbon-12, the mass of carbon-12, and the mass of the constituent parts. And that difference, so let me change colors here. You guys can see this. So you take your 12.09558 and subtract 12, right? You get 0.09558 AMU. That represents the binding energy for carbon-12. That is the energy needed to keep carbon-12 together. And if you were to happen to pull carbon-12 apart, right, that would be the energy that you would see released. Or, if you try to cram it together, that's what you would need in order to cram it together. So this is the thing. All right, now I was being a little hasty there because it's not actually energy, right? That's mass. Okay? And so I want to go back to the slide here and show you that this number down here, this 931, it's actually 931.5, is important. So what that is, let me make myself big. That 931, it's actually 931.5, is the energy, right, contained in, that's per AMU. In other words, let me erase this. 1 AMU is equal to 931.5 MeV of energy, mega electron volts. which is actually a lot. So even though you just have a little bit of mass, it doesn't look like a lot, 1 AMU is equivalent to that. So if we take our 0.09558 here that we got and we multiply by 931.5, it's going to be a big number. I get 89 point something, 89.03. Mega electron volts of energy. So that is the energy. So I apologize there. This is the mass that represents that amount of energy, right? And of course, E equals mc squared is the equation that discusses this. Make myself small. An interesting note: that equation is not the full equation. Minute Physics did a really interesting video, and I urge you to go watch his stuff because it's really good. And I have it on my site. That's not the whole equation, and so I think you ought to check that out just to take a look at it. But it's pretty cool. But anyway, in my notes here, right, here's an example of how to do this problem using E equals mc squared, which essentially is what we're doing. Okay, and there you go. Here it is in picture form. This is a helium atom here, and then you can figure out how much binding energy it takes to keep it held together. And so this is a thing. Here's a graph. I'm going to show you this, and you'll see this in a lot of textbooks. The larger the binding energy is, the more stable things are, and so this is why we end up using certain nuclei for, nuclear reactors or weapons and things like this. But anyway, in these notes I have more examples, and I urge you to go look at the notes because I put examples there, which I think are pretty good. So anyway, these are examples of this principle. On a final note, I need to defend Einstein here. He figured this out, and then they used this. Of course, he urged at the time that we need to be making these, weapons in order to try to end the war. And they used this knowledge to do that, and of course we've had nuclear weapons ever since. This was World War II, and people, I think, still blame him for a lot of the things that happened, which, to be fair, he did in fact call for the use of these things, that we needed them and this and that, and I think he recanted that later. But he didn't make this up. This is all naturally occurring. I think blaming him would be like falling off of a tall object and blaming Newton for figuring out how gravity works. So that's kind of silly. But anyway, I think it's a fascinating topic. I hope you do too. Thanks for watching.